And here we are. I guess it's time to begin. Hello, everybody. Welcome to Modern Android Development. I'm Chet Haase from the Developer Relations team. And I hope Romain can hear me. Apparently the audio is very quiet on his side. Hang on, technical
Hey,
difficulties.
Chet, sorry, I can't. Sorry, I have no audio. Can you say something?
I can speak to you now.
Okay, now I can hear you.
All
So
right.
you were talking and nothing was coming out. So maybe you want to try it again?
maybe I wasn't speaking at all. It was all a very clever joke. And I'm getting delayed audio, which is super annoying.
All right. So I am Romain from the Android Toolkit team.
All right, and let's begin this talk. I'm hearing myself a second after I speak, so I'm going to see if I can manage this. Hello and welcome to Modern Android Development. We have given this talk in various forms over the years. In fact, this is not the first time we've said Modern Android Development. In fact, a couple of years ago, we gave a talk in Paris called Modern Android Development. A week after that, we gave another talk in Paris called Modern Android Development. Then at Google I/O that year, we gave a talk called Modern Android Development. And then at Android Developers Summit in the following year, we gave a talk. We also gave a talk in Greece and probably one or two other places. So the question is, why are we doing this again? Are we just reusing the content again? Fortunately, we're not. We actually meant something different by Modern Android Development at that time. The talk that we gave at that time was basically saying, here's what we used to tell Android developers, and here's how things have changed over the years, and these are some of the common best practices that you should take as developers now. But now we mean something specific about modern Android development. We mean the set of technologies, most of them quite optional, that everybody should learn and use to make it easier to develop your Android applications. So modern Android development is our attempt to sort of paint a cohesive surface area around what those technologies are. First, why don't we talk about classic Android developments and figure out where we came from.
All right, so just we're going to start with a bit of a history lesson. The first public version of the Android SDK was released at the end of 2007, November 2007. It was called M3 for Milestone 3. So they were Milestone 1 and 2, but they never made the day publicly. And if you download that SDK today, you will find inside of it a lot of things that you already know. For instance, we had intents and activities. A lot of the fundamentals of Android programming were already there. But for the purpose of this talk, we want to focus on a few things specifically. So first, the Java programming language. That was already the main language as part of that SDK. Some of the platform APIs I just mentioned, intents and activities and so on, were already there. So we're not going to talk about that very much today. The tools were different. So if you started Android in the past few years, Android Studio. Instead, we are using another IDE called Eclipse, and we're going to talk about this in more detail. And finally, APKs were already the way we were distributing applications. After this release, a year later, in November 2008, we had the first public release for users, so Android 1.0 with our first Android phone. And then for many years, nothing very interesting happened, actually. So the teams were really busy at work, and Chet will talk about that in more detail. But as far as we're concerned for today's topic, nothing really changed, right? We didn't introduce new programming languages, we didn't change the fundamentals of the platform. And that is until 2013 when we announced and introduced Android Studio, so a replacement for Eclipse. Then again, not much happened. Actually, a lot happened, but no fundamental shift until 2017 when we added support for the Kotlin programming language at Google I/O. It was followed by the introduction of Arch components and Jetpack, and then app bundles that we'll cover in more detail later.
So meanwhile, on the language side, we classically had support for the Java programming language. There were a lot of really good reasons for us to choose that language for the primary development language for Android. many, maybe even most developers in the world already knew the language. So we were introducing a new platform and asking developers to come on board and write applications for that platform. One of the tricks in doing that is to make the barrier to entry as low as possible. So if we could use a language that developers were already familiar with, then they didn't at least need to learn a new language just to then go ahead and learn new APIs and new ways of programming to this new kind of device. So lots of developers knew the language. That was great. There were free tools. This was really important because, again, lowering the barrier to entry included making it easy and cheap or even free for developers to actually come on board, right? We didn't want everybody to have to buy a development kit for this platform. We just wanted them to go ahead and write code and ship applications. So the fact that we could use the development tool, the IDE, and the plugin for Eclipse was really important. There were a lot of libraries and practices and ways that people wrote their programs and middleware that they used that they could just bring over wholesale or at least in some form over to this new world, and that was really powerful as well. And there was, now this is a little bit dated right now because most modern languages have memory management unless you're down at the lower levels like C and C++, but Java, the programming language, offered the idea of this runtime where it would manage your memory for you. You didn't have the problem you do in native code of you need to allocate memory before you use it, you need to free that memory later to avoid leaks, and you need to not use the memory after you've freed it if you want to avoid crashes. It's something everybody deals with, but if you can remove that headache and make it automatic instead by using a runtime and a garbage collector, it just simplifies a lot of the programming effort in writing complex applications.
All right, so we mentioned the tools, and in particular Eclipse. So Eclipse was not only, or is not only an IDE, but if you're not familiar with it, it's also an application platform. You can use it to build something that's not an IDE. Eclipse as an IDE is a collection of plugins, and we had our own plugin called ADT, so the Android Development Tools. The reason we picked Eclipse was twofold. First, it was free, and still is, and developers were extremely familiar with it. It is still a very popular IDE amongst Java developers. So it made sense for us to lower the barrier of entry into mobile development, to go with something that people already knew. Of course, I already mentioned it was free, but very important, especially for folks who are starting. And Eclipse gave us a way to integrate our tools within the rest of the IDE. There were some limitations that we're going to talk about, but at least it was free.
And on the API front, in classic Android development terms, we had the platform APIs, right? We had all the stuff that shipped with the platform, which is really powerful. Applications could, developers could write applications that would access these platform APIs, but they didn't need to bundle all that stuff with their applications. They could have these minimally sized APKs and depend on the stuff that was actually sitting on the user devices. We had many, many releases very frequently. We'll see that in a couple of minutes here. Really frequent in the beginning. There was a lot of sort of stunning new functionality in every release because the team was running really fast to catch up to where they needed to be, both for developers and functionality that developers needed to write these applications, as well as users and what they expected in a good, robust mobile experience. There were bug fixes aplenty, of course, because writing software means writing bugs, and then you need to write more software to fix those bugs. So racing to get all these things out as quickly as possible. So if we take a look at a timeline, we can see some of the timing details involved there. As Romain said earlier, 1.0 came out in late 2008. Just a couple of months after that was the first dot release with some important fixes. Then there was the Petit Fleur release, 1.5, again, just a couple of months after that. And then 1.6 came out, 2.0 came out. And you can see, look at the time between these releases. These were like even as little as a month between these releases. And oftentimes, these releases were actually being developed in parallel. So developers on the team were working on 2 and sometimes even 3 releases in parallel because there was so much new functionality and important bug fixes going into each one of these. So race. But then finally this came down to sort of a normal annual cadence, and everybody breathes a sigh of relief. The people on the development team not having to run as fast and as hard to get these things out on a continuous basis, but also developers consuming the functionality and coming up to speed on what the new APIs were, as well as partners and manufacturers and even users like not having to absorb all this new stuff all the time. It's a little bit easier for manufacturers to absorb things on an annual basis, qualify these releases, get them out on their devices, get out new devices with the new functionality, whatever it is. So now we're in more of a regular cadence on a year-by-year basis.
All right. As developers, of course, what you care about is putting your application in the hands of users. And so distribution is a very important component of your developer workflow. Since the beginning, like I mentioned before, we've been using this format called the APK, the Android packages. What's interesting about APK is that they're nothing more than a glorified zip file. It's just a zip file with a different extension. And just by convention, what we find in the zip file is what makes an Android application. Which means like it's a very simple format and it was very easy to manage. It still is fairly easy to manage, but there were some limitations, mostly due to the needs of the time, right? Like when the first Android phones came out, we only had one screen size, one configuration. There were only phones. We didn't have tablets or TVs or watches or stuff like that. So APKs were not really meant to hold more than one configuration. We had support for multiple configurations already in the APIs. But having multiple configurations in the APK meant that you would either have to create multiple APKs for your app, or you need to create a single large APK for the application.
All right, so now let's talk about some of the problems that came from these classic development patterns that we used back in the day. On the language side, as I said, we had the Java programming language. It's still a great language, but it is verbose, especially compared to newer languages that have come out in the last few years.
Yeah, so we mentioned Eclipse, and it was very powerful, especially being an application platform. One of the issues, however, is that it tended to be difficult to customize because Eclipse was meant to be so generic. It made the job of the tools team a little harder. It also meant that all the subtools were designed and implemented by different teams and different companies. So the UI tended to be a little less consistent than it should have been. And more importantly, at some point, a lot of the efforts for Eclipse went into the platform itself and not really the IDE. I mean, the IDE was still making progress, right? But not necessarily in the areas that we, Android, cared about, which was kind of an issue. And we had no control over the direction of the IDE, which made it very difficult for us to improve the core user experience. Eclipse remains a very good tool. It just was not like the best solution for our own needs, which is why eventually later we switched to Android Studio.
On the API side, as I said before, we had all those lovely platform APIs. The problem was that developers were necessarily limited by what the users could get, right? So more and more we would tell the developers, hey, here's this exciting new functionality and these important bug fixes. And the developers would say, that's lovely. And we'll get back to that in 3 or 4 years when my user base has devices that can actually use those features, because we couldn't control when these releases were going to get to those user devices. Now, it's important to realize that like some of the success of Android certainly comes from the fact that we distribute a platform and we don't control what manufacturers and partners do with it, right? So it is up to them to determine when to send that out. And there's a flip side to that coin. On one hand, it means that the manufacturers and partners feel like they are in control of their own devices and their own consumers, and that's great. And that allowed them and enabled them and got them excited about adopting Android for that platform. On the other hand, we can't tell them when to ship those releases. So we couldn't determine exactly when users would get these releases. Therefore, it was difficult for us to push new functionality to developers and developers to take it on board really quickly because of that dynamic of not knowing when the users were going to get that stuff. Also, some of the early APIs were complicated. Now, to some extent, this is kind of necessarily the case because here's this platform that has everything from local storage to cloud storage to local capabilities to the ability to talk to anybody on the internet anywhere to do, website stuff. You can deal with cloud, you can deal with graphics, you've got constrained screens, you've got constrained battery and energy that you probably shouldn't use too much of. Like all of these capabilities, you have to get in your mind and then get in your application. So it's a bit of a complicated space to develop for to begin with. But also some of the early devices were so constrained that those constraints then fed into the APIs and made APIs that were maybe not as easy as we would like in the long run. But also just some of the things that developers need to do to write these applications in this complicated space were difficult. And some of those things include lifecycle, knowing when your application is going to be killed, knowing when your activity is going to go in the background so that you don't leak things or access things that have gone away, storage, whether you're storing locally or in the cloud, navigation, the up versus back, and how you actually navigate to the different screens in your applications. There's a lot of stuff going on there. And the more functionality we built in, the more APIs we had, the more complicated it got.
And speaking of complicated, so I already mentioned that APKs were not designed to handle a ton of configurations at the same time. They could, but what it meant for you is, again, either you created a monolithic APK where you put all your configuration, which meant putting all your resources into one APK, which meant your users had to download all the resources, even the resources that they would never ever need or use on their own device. And with devices that were limited in terms of storage, or even with users that had limited bandwidth, that was not ideal. The other solution was to create multiple APKs, but that made your life harder and more complicated because of course you had to manage those multiple APKs, uploading them, managing them, creating them in your build script. So again, not ideal.
So the answer to these problems, increasingly over the last few years, we've come out with these technologies that we are now labeling modern Android development, which we define as the set of development tools, APIs, language, and distribution technologies recommended by the Android team, including us, to help developers be productive and to create better apps that run across billions of devices. And there's a couple of important parts there. One is that there are these 4 areas that we just talked about for classic Android that we're going to cover now in modern Android development. And running across billions of devices means all of the technologies we're going to talk about are things that you can adopt outside of the platform, right? So things like APIs that come in unbundled libraries that you can then package with your application so that you have full control over the capabilities that the user has, because you are no longer dependent upon which release they're on and what capabilities lie in the underlying platform. So the pillars that we're going to cover, again, internally we talk about the pillars of modern Android development. So of course I'm an engineer, so I wanted to draw a diagram talking about modern Android development. I actually drew pillars because that's what they said. I'm kind of literal that way. So you can think of modern Android development as encapsulating the pillars of language, tools, APIs, and distribution. And then underneath that is this platform that we just kind of take as read. We're not going to talk about the platform APIs. We're not going to talk about all of the play technologies, including the dashboard and the console and that stuff, because we assume that you're using that stuff. That is not what we're calling modern Android development. It doesn't mean you don't use it. It means you use that stuff. You need to understand that stuff. But on top of it are these modern Android pillars, starting with Kotlin.
Kotlin, the programming language. So ideally, we would see you, the audience, and we could ask how many of you are using Kotlin. So we'll assume that about 60% of you are doing so.
Wait, you can see one
Kotlin.
person, and it's me, and that's 100%. So
I also use Kotlin. Anyway, so here's the timeline of Kotlin on Android. So Kotlin is a programming language that is designed and developed by JetBrains. So JetBrains is the company behind IntelliJ, and IntelliJ is the foundation of the Android Studio IDE. So in 2016, JetBrains released the version 1.0 of Kotlin. And a lot of folks, both internally on the Android team and externally, like amongst the developer community, had been paying attention to Kotlin over the years as it was maturing and getting towards 1.0. But once it hit 1.0, more and more application developers, more and more of you started using Kotlin and started using it in production. So we started looking at it even more seriously internally, which led in 2017 to the Android team announcing at Google I/O that Kotlin was now an officially supported language for Android. So we're going to talk about that in more detail, but basically what it meant at that point was we're going to make sure that we do not break your workflow. Let's say when we update Android Studio, we're going to make sure that we don't break support for the Kotlin compiler or whatever plugins that you might need for using Kotlin. And then, we started using Kotlin internally as well, like in some applications, in some libraries. We're going to get back to that. And last year in 2019, we announced that that Android is going Kotlin first. And again, we're going to talk about what this means exactly. But we've been investing more and more into Kotlin in different areas. And finally, earlier this year in 2020, there was no Google I/O, but we had the Android 11 beta launch. And at that time, we announced that coroutines are our preferred way of doing asynchronous programming. It's not the only way. There are other ways, and they work just fine if you like using those other solutions. But we think that coroutines are a great way to get started. So one question that you might ask if you're not using Kotlin already is why Kotlin? So there are many reasons. We just want to focus on 4 of them. So first of all is the expressiveness of the language. You don't have to write as much boilerplate. It's a language that's very easy to read, very easy to maintain. It also brings increased safety to your code. So most of it comes from the nullability at the language level. So that's part of the type system. So a type that's null and a type that's non-null are different types. And the compiler can infer that you're doing the right thing in the right places. One of the most important features for us was and still is the interoperability. Most of the platform APIs on the Android platform are written using Java. So we have Java APIs. And Kotlin not only can compile to the same bytecode that we use on Android, but it can also call into Java APIs out of the box without doing anything special. And you can go the other way around. You can have Java programming language code call into Kotlin without doing too much and most of the time doing nothing. So that part was extremely interesting for us because we wanted to make sure that if we adopted a new language, you wouldn't have to rewrite your application from scratch, right? So with Kotlin, you can decide that the next class you write, not even the next screen, not even the next file, just the next class that you write can be written in Kotlin. You don't have to rewrite everything. You can do that over time if you want, or you can keep using both languages for however long as you wish. And finally, I already mentioned coroutine, but support for structured concurrency. So it's elegant asynchronous programming. It's avoiding callback spaghetti. We're not going to go into coroutines in this talk. This is a very complex and deep topic, but coroutines are a fantastic tool for developers. Well, let's look at a little bit of code. So here's a very short example that highlights some of the features of Kotlin. There are many more features that are interesting to look at. But first, if you look at the onCreate method on this activity, you can see that we take as a parameter a bundle question mark. So that means that we are getting a value that could be null, but null without a question mark would mean that this value is never null. And we're going to get back to that. We're adding support in the platform to help Kotlin developers in that space. But it's great because if you have a non-null type and you try to assign null, the compiler will yell at you and you will avoid a null pointer exception at runtime in your code. Then support for lambdas. So lambdas are not something specific to Kotlin. They exist in many languages. A great thing about Kotlin is this specific syntax that you have at your disposal where when the lambda is the last parameter of a method, you don't have to pass the body of the lambda inside the parentheses of the method call. Instead, you can open the curly brace at the end and you can put the body of your lambda right there. In a way, it almost feels like you're extending the language with your own features. And many DSLs or things like Jetpack Compose make heavy use of that to make the code easier to read and easier to write as well. Another good feature, again, not specific to Kotlin, but it's nice to have it, is our extension functions. So here we have a string called name, and we call the method capitalize on this. That method is not part of the string type. Instead, it is a method that's been declared in the application or in a library, and it's actually just a static method that takes a string as a parameter, and thanks to some syntax magic at the compiler level, you can invoke that static method as a regular method on the object itself. So this is a great way to keep your data types as simple as possible and to push all the complexity of the logic in other areas. So you have to do specific imports to get that logic brought into the application. What's also very interesting for us is that it allows us to create new APIs for existing types that are part of the platform, for instance. We're going to talk about that in a minute, but we have this series of libraries called the Ktx libraries, the Kotlin extensions, where we do provide all those extension functions for existing platform APIs, so they are easier to use when you're a Kotlin developer. Template expressions, again, not new to Kotlin, but very powerful. You can use expressions directly inside strings and they get interpolated. It's a much easier way to build strings rather than concatenating different strings yourself or using string builder or string buffer or stuff like that. And finally, there's this nice syntax helper to access properties. So when you have getters and setters on the Java side, for instance, you can just use this dot notation. So you can say dot foo equals foo. That will call the setter. If you just do dot foo, it will call the getter. It's a very clean way of writing and reading code while maintaining the safety of having getters and setters, so you can do whatever checks that you might need to do in those implementations. Another big reason why we like Kotlin is speed. And here we're not talking about speed of execution at runtime, right? Like that's a different matter. We're talking about speed of development. You have to write less code. It's easier to express what you want, but also the speed of the language evolution. Kotlin is constantly improving both the language and the runtime library. A great example are coroutines. When Kotlin 1.0 came out, it didn't have coroutines. The coroutines themselves went 1.0 like a little over a year ago, and since then they already gained new features like flows, for instance. And things like extension methods that are already mentioned are also a way for us to evolve things outside of the language itself. And we work very closely with JetBrains on the language itself. I mean, they own the language and they set the direction, but we have people at Google working on the compiler, for instance, so we are helping with this evolution as fast as possible. And we've been very happy with Kotlin so far. I mentioned earlier that, I assume that 60% of you use Kotlin, and this is why. So this is data as of May 2020, so the numbers are actually probably higher now. But we know that amongst developers who do Android development for a living, 60% of them are currently using Kotlin already. And if you look at the top 1,000 apps on Play Store, so the most downloaded apps on Play Store, already 70% of them use Kotlin in some form. So it's been a huge uptick considering that we introduced Kotlin 3 years ago, and it has become like our Kotlin first approach is only a year old. So speaking of Kotlin first, so here are some of the initiatives that we've been working on in that regard. So first of all, tooling. We've been adding lint checks just to make sure that we can help you write idiomatic Kotlin code, make sure we can help you catch things that are not as performant as they could be. I mentioned that we work with JetBrains, so we have a dedicated compiler team. So it's the folks who work on R8, so the R8 optimizers, and they've been implementing Kotlin-specific optimizations in R8. And when I say Kotlin-specific, is looking at the kind of bytecode generated by the Kotlin compiler. We've been able to optimize the output of the Kotlin compiler because the behavior can be different than the regular Java compiler. We've also been working on annotation processing speed. So a few months ago, we announced KSP, the Kotlin symbol processor. It's a replacement for KAPT, the Kotlin annotation processor. It's just a faster way of processing annotations. It's even better if you don't do annotation processing, but if you really have to, you can take a look at KSP. Type safety, again, something extremely important in Kotlin and extremely useful. So we've been slowly annotating more and more platform APIs with this @nullable and @non-null annotations. They're useful both to Java developers because in the documentation we can show you, okay, this is not supposed to be null. Please don't send null. You're going to have a hard time at runtime if you do that. But it also helps the Kotlin compiler because the Kotlin compiler can take those annotations and treat those types as if they had been declared in Kotlin. Now, a little twist on that is that we also have these @recently nullable and @recently non-null annotations. And those, instead of causing a compilation error, like nullable and non-null, will cause a warning. So we use that when we add the annotations to type at first, and then later on, we replace those recently versions with the regular annotations so they turn into errors. Just a way for us to help you get ready without breaking your compilation right away. I mentioned the Ktx library, so the Kotlin extension libraries before. We have a number of them now. And again, they're a way to improve the platform APIs outside of platform releases. And they focus on what we tried to do with those Kotlin extension libraries was not to add like every single feature we could think of, right? I remember like some folks were submitting code to those libraries for instance, to add the ability to take a picture with the camera on the context object. The goal of this libraries is really to use features of the Kotlin programming language that are not available to Java developers, so that when you use Kotlin, you get a more Kotlin-like experience using the platform API. So let's take a look at an example that's using an extension function. So on the platform, we have this create bitmap API on the bitmap class. It takes a width, a height, and a configuration. And let's say that we want to turn a drawable into a bitmap. So we need to draw the drawable into that bitmap. So on the drawable API, we have this draw method. It takes a canvas. And here's the kind of code that some of you may have already written several times to turn that drawable into a bitmap. So first of all, we need to take the bounds of our drawable and remember them. Here you can see another cool feature of Kotlin. It's the destructured assignment, where we can split an object into its more fundamental components, in this case, the coordinates of the rectangle. Then we're going to set the bounds of the drawable to match the bounds of the bitmap that we want to draw the drawable into. Then we create our bitmap, we specify the width and the height, and 90% of the time your configuration is going to be ARGB 8888. Finally, we can draw the drawable on the bitmap by wrapping the bitmap into a canvas, and we restore the bounds. So it's not difficult. It's just a lot of code that you have to write that's error-prone, and that probably either you create a utility library or you rewrite that code over and over again. With the Ktx libraries instead, we have an extension function on drawable called toBitmap. And as you can see, it makes use of yet another feature of Kotlin, which is the default values for parameters. So the width, the height, and the configuration have default values, so you don't have to specify them. But with this extension function, all the code that we saw at the bottom that you put in your app just turns into this. So you just call drawable.toBitmap, you pass the width and the height you want, and those are optional if you just want to use the intrinsic width and the intrinsic height, and that's it. So much easier, much simpler, and makes great use of Kotlin programming language features. There are many, many more Ktx extensions. If you're not using those libraries, I highly recommend you take a look at them. So other things we've been doing with Kotlin, we started working on Kotlin-specific APIs. So for instance, in Room and Work Manager, we now have support for coroutines. It makes asynchronous programming a lot easier. If you're interested, we talked about this in some episodes of our podcast, the ADB Android Developers Backstage. Paging 3, so Paging 3.0 is a complete rewrite of Paging 2.0, and it's been rewritten using Kotlin, including support for coroutines. And of course, if you already know about it, Jetpack Compose, which goes even further. Not only is Jetpack Compose written entirely in Kotlin, it also relies on a Kotlin compiler plugin to work. So I highly recommend you watch some of the talks that we've given about Compose if you want to know more about this particular step in the process. And finally, and that's thanks to Chet and his team on the DevRel side, we've been focusing a lot on documentation and training. So we have new documentation, we have samples, we have code labs, we have courses, we have tons of articles and videos. For instance, recently we had this Kotlin vocabulary series that explains some of the concepts that are common in Kotlin. So for instance, if you want to understand like coroutines or some features of the programming language, you can take a look at this series.
All right. So let's talk about APIs. And when I talk about APIs, I'm basically talking about Android Jetpack, but not all of Android Jetpack. Jetpack is a set of like over 80 libraries now, and they're all updated every couple of weeks, and they're available in various versions all the time. But we're specifically talking about a small subset of Android Jetpack APIs, specifically those APIs that were created by looking at the pain points of Android development and figuring out what we could do to make things a lot easier in general. So I think of this as starting with Constraint Layout, which came out in 1.0 in 2017. We'll see a little bit more about Constraint Layout soon. And then Architecture Components is really the foundation, it's the core of all these modern Android APIs that I'm going to talk about. And that started out with Lifecycles, View Model, and Room, making it a lot easier to deal with Android lifecycles as well as local persistent storage. And then at Google I/O, we announced more architecture component APIs, the paging API, which Romain already mentioned, the navigation API and tool, as well as Work Manager and we'll hear more about those soon as well. Material design components made it easier to adopt the spec. So we'd had this material spec ever since Lollipop, and it had evolved into Material 2. And it was great to have somebody define, what applications could look like. And here's a standard and common design language that everybody can use to create these applications. But we kind of left it up to developers as an exercise for the reader to actually figure out how to translate that design spec into application code. Material design components made that a lot easier by introducing these components, these views that you could just take on, and they inherited a lot of the attributes we were talking about in the design spec itself. And then at Google I/O the next year, we announced Jetpack Compose being developed in the open. That was pre-alpha at that point, but in this past August, Jetpack Compose has gone into alpha and development continues apace. We also introduced the Ktx Library, which is currently in beta that we'll probably hear a little bit more about later. And then finally, Motion Layout came out just recently, along with the editor that went stable in August, I believe. Motion Layout is a subclass of Constraint Layout that makes it a lot easier to create these rich animations in UIs. So let's look at some of the details. For Constraint Layout, I think of this as being sort of relative layout plus plus. It gives you all the capabilities of positioning views relative to each other, which is the important aspect of relative layout, but that's kind of where relative layout stops. Constraint Layout goes much, much further, gives you the ability to, say, define these key lines, these guidelines in your app, and then align relative to those, as well as all kinds of utilities for chaining and expanding these sets of views, or even flowing views onto the next lines, like really powerful capabilities that you want for a general purpose layout. But the best part is it was developed in concert with a tool. So we always had a design tool in Android Studio that kind of worked. And that was about as good as we could get, because the APIs were developed much earlier than the tool, and the tool really couldn't get a lot of the capabilities that it needed from the APIs. There just wasn't a really good communication mechanism. But Constraint Layout was designed from the beginning to actually work in concert with this tool. So you could easily go back and forth from using the design tool to going directly into the XML, whichever side you wanted to operate on, or ideally both. And it works very well for that. Speaking of tools, we also came out with Motion Layout, as I said, a subclass of Constraint Layout. You can think of Motion Layout as being the next evolution of transitions. So transitions is this idea of having a before and an after state for your UI, for your layout, and then the system underneath will figure out how to animate between those. Just an automatic animation to go from before to after. But that's where transition stops. Motion Layout takes it much further in a couple of ways. One is that you can customize these animations and create this really powerful animation experience going from that before to that after, and integrate it with user feedback. So you can think of like a user scrolling a feed on the screen as being basically scrubbing the animation of whatever you define the Motion Layout animation to be for that UI. But again, more importantly, just like Constraint Layout, it was developed in concert with a tool. So Constraint Layout is a little difficult to deal with if you're only writing XML. That's why the tool is really powerful. Animations are like, an order of magnitude more difficult if all you've got is XML code to write. So you really want to be able to use this design tool to preview what your animations are like and tweak things in a visual way. And again, go back and forth between XML and the visual tool if you'd like. On the lifecycle front, this is what Android developers needed to understand and memorize, and it was actually a lot more complicated than this. It's important to know when your application is paused, when it's not there at all, when it has started, and in order to do that, you then needed to subclass activity or app compat activity, and then handle all of these methods, all of these overrides, because there was no other way for you to get the information that you really needed. And the impact of this was people had put entirely too much code in their activity itself. It was not meant to be a monolithic component of how you architect your applications, but because of the way the APIs worked, that's kind of the evolution of how Android code came to be. And then you'd have this spaghetti code in activity classes, because this is where people had to start to understand where the state was at. So now we have a new model. I would say you still kind of need to understand what the states of applications are, so you should have some general idea of life cycles. But the new approach is to observe. So now app compatibility as well as fragment both allow you to call them and say, I would like to observe on lifecycle changes. And then with that observer, you can receive callbacks and find out what is going on in your lifecycle. My favorite part is you can actually query what's going on in your lifecycle. At any point, you could actually call and say, hey, am I paused? Am I started? Am I resumed? Which you could never do before. The framework always had that information, but for some reasons that escape me, we never actually exposed that. There was no way for you to find it out, which is why you needed to override those methods. So now you no longer need to override the methods. You can observe and you can find out at any given time what is going on in the life cycle. So all of this has led to an evolution of an architecture that makes a little more sense. It's easier to encapsulate your UI away from your data, right? So you should have your model code over here doing whatever it needs to do with your data, and your UI code somewhere else, so that the two don't mix too tightly and then get confused and create this pasta. So what you do now is you have the UI code and it registers an observer, and then when there is a change on the data, it will send in a callback and you can do whatever you need to on the UI side about that. Typically, you would have something like a database sitting underneath this thing, and maybe you're using Room sitting on top of SQLite to observe this, and then it can send information in a live data object, and then the UI can query what the value of that object is and do the appropriate thing. In Room, the API looks something like this, where you have this DAO where you can now do these queries, and you can do insertion and deletion. And the important thing to note here is these are now, through Kotlin, exposed through these suspend functions, which is really powerful, because if you're talking to the database, whether you're querying or whether you're actually changing values, you shouldn't do that on the UI thread. That's pretty obvious. We've been saying this for years, and it's probably obvious anyway. If it's a potentially expensive operation, get off the UI thread. But that means it's up to you to figure out how to do that. And that is where the spaghetti comes from, right? Because now you need to have another thread somewhere else that you can foist this work off to. And then as it progresses, or when it finishes, it's going to call you back at some random place in this other code, random time. And then you need to figure out how to do this in a way that the architecture of your application actually makes sense. And coroutines and suspend functions in particular make this a lot easier, because now you can call the functions that you need to actually do the database transactions, and it handles the tedious details of actually putting it off on the correct thread, and then suspending until it has the answer that you need, and then returning to the code that called it. So it's a much more reasonable way to write the code, and it also makes it a lot easier to actually reason about what is going on in the code. So then we have all of these libraries that came out, these architecture component libraries that came out that work well together. So all the stuff inherits the capabilities of the life cycle. So we have common ways of working between all the different architecture components. We also have the ability for Room, as Romain said before, to use coroutines and flow to make all of this easier to deal with in writing the code and then maintaining the code. But it's important to note that we're not ignoring other approaches that developers have. So if you already have RxJava in your code, RxJava solves many, many problems, including some of the lifecycle problems that we have here. But the flip side is it tends to inhabit all of your code, right? It's an architecture approach that you take on when you take on RxJava that tends to send its tendrils into a lot of places in your code. So maybe you're thinking, yeah, this lifecycle stuff looks nice, but I'm already using RxJava and it's hard to extract myself from it. And maybe you're doing other things with it that are beyond what lifecycles offer, and that's fine. We also expose APIs, assuming that people may have RxJava solutions out there, and we want to make it easy to continue using those if you choose to. So not a problem. Navigation component APIs are a powerful way of helping you create and manage the flows through your application. So typically, especially in these small screens, we have these separate windows, these separate screens that define the different things that you can do in your application. We have a message list versus a message. We have the shopping experience versus the cart versus the payment transaction, whatever they are. It's always been sort of a requirement of any large application or reasonable size application to be able to have these different screens and then navigate between them. Not only over to the cart, but then back from the cart. And what does it mean to go up versus back in an application? All these complicated things. And it was up to you to actually do that in your code. Navigation component takes those patterns and embeds it in both an API as well as a tool. And what I'm showing here is in Android Studio 3.6 and up, we now expose navigation component, all the pieces that you need in some of the standards templates that we offer. So if you create a basic activity, you will automatically get an activity with 2 destinations built in. Now, you probably don't need 2 destinations. You may need 17 or 1 or whatever it is. That's fine. Just rip out the thing you don't need, but it at least gives you the sandbox, the playground to put your code and your approach and your architecture in. I kind of like it because it pulls in all the dependencies that I need, and I don't have to think about where to go to get the different pieces. So you create one of these, you get the 2 destinations built in, and then underneath, of course, since it's Android Studio, and this tends to be how design tools work, you have underlying XML code. So these 2 are equivalent. We have the 2 destinations here that are defined by default as 2 fragments, and then inside of those fragments are these actions. So if you look at the design tool, you see these arrows. That basically defines which destinations we can navigate to from other destinations. This doesn't take us to that thing. It just says, here is a destination that can be navigated, and then we actually write code to do the navigation. So those actions inside the fragments define the navigation that can happen from and to those destinations. And then we write code something like this at runtime. Somebody clicked on the thing that's going to take them to that other destination, and then we say, okay, navigate to this thing that is automatically defined in a resource for us according to what we did in the design tool. There are several other things that are important to note about navigation. Looks like I'm going to have to rip through. We are running really short on time, so I'm going to run really quick. Lots of different capabilities. I would suggest you check out the Mad Skills. The first series of skills episodes that we had were all on navigation, talks about some of these new capabilities in navigation. Work Manager is a powerful architecture component library that allows you to have deferred and guaranteed background work in a single API. So it kind of takes the place of many approaches that developers had for handling this kind of situation, depending on what release you were on, whether you had play services, whatever it is. Goes all the way back to API level 14 with a single API that you can use for all of this. Here's a use case for Work Manager where you can say, okay, it also builds in the ability to have constraints. So I want to run all these filters, but not if the battery's too low. I want to compress it if you have enough storage, and then I want to upload it based on the metering constraints of the network that we're on. You create this job, you create the constraints around that, and then you bundle the constraints with the job, and then define the timing characteristics. I want to run these things at the same time, and then I want to run this other thing. And then upload. We also make it easier to integrate with foreground services, which is increasingly important as we need to expose information to the user about the things that are going on in the device, and foreground services can be used for that. Camera X, currently in beta, makes it a lot easier to write camera applications around specific use cases. Doesn't take the place of the entire camera to API, but it makes it much simpler to do the things that honestly are the things you wanted to do to begin with. It also makes it easier to cover camera capabilities across the ecosystem, because we take the workarounds that you were having to build into your application, we put them directly in the library to handle situations that we knew developers were running into in the diverse ecosystem that we have in Android. Really simple code here. You can capture the image, you set up a target resolution, and it just does the right thing for you. This even this step could be tricky in Camera 2, where if it didn't have that exact resolution, then you would need to iterate through the choices and figure it out, and Camera X does that for you. It also deals with life cycles, so you don't have to worry about closing the camera, closing the device, making sure to free that at the right time, and then you just take the picture that you need. At the same time, lots of these releases all the time coming out in alpha, beta, RC, and stable releases, and we're developing new capabilities all the time. And Romain is muted.
Yes, very quick Android Studio. Skip to the end of the timeline, please. So we announced Android Studio in 2013. Basically, we've added a lot of things in Android Studio, and I want to draw your attention to 2 things. One is we have a number of profilers now, so CPU, memory, network, energy profilers. We also added support for the systrace profiler, which is a system-wide profiler system. And then we've done things with navigation editor, motion editor, the constraint layout editor, and view binding, where we developed the libraries in parallel with the tools. This is something that we didn't do early on Android because, well, we were pretty busy But that led to much better tools, right? We designed the libraries to be toolable, and the Toolkit team and the tools team work together to make sure that we deliver a great experience this way. Meanwhile, yeah, so instead of using the Eclipse platform, now we use IntelliJ, which has enabled a lot of interesting things for us. JetBrains have been an incredible foundation that we can build upon. In particular, we get amazing support for Kotlin and Gradle out of the box. And we have great collaboration. You know, I mentioned that we work with JetBrains on the Kotlin compiler, but we also work with them, obviously, on Android Studio and IntelliJ. So there's a lot of like tight integration. And of course, like I mentioned, we try to integrate new APIs with the tools as early as possible to provide the best developer experience possible.
Android app bundles, again, ripping through really quickly. Basically, make your application smaller. Otherwise, people are going to uninstall it from their phones. They don't have as much storage as you assume they do. And that means that when they install a new application, they're going to uninstall an old one. So the smaller you make your application, the more likely it is that they're going to keep yours on their phone. Also, the more likely it is that it's going to succeed in actually downloading and installing in the first place. The smaller it is, the more likely it is that people are going to install. The difference between APKs and App Bundle is it's kind of like a monolithic APK, except on the Play Store side, it will compile an APK on the fly and download only what it needs. So it's kind of the best of the monolithic, best of both. It's a monolithic APK that can actually create the custom APK depending on the runtime configuration that the user needs. Lots of people adopting this so far, even more since next year, since in August of next year, new applications will be required to use app bundles, but I would encourage you to check it out in the meantime to get up to speed on it, and also because on average, developers are seeing a 20% size savings over the same monolithic APK that you might be shipping today. So we've talked about these 4 pillars: language, tools, APIs, and distribution, which are basically Kotlin, Android Studio, all of those APIs, and app bundles for distribution. You'll learn more on these sites, d.android.com, modern Android developments. And also there's a Mad Skills series that's teaching more technical details about all of these things, starting with navigation, then into app bundles. And then just this week, we started a series on material design components. And that is all the time we have. Thank you.